Hello and welcome everybody to today's course about protection in electrical power systems. Today's lecture is about earth fault protection and here especially about the earth fault calculations, because we must be able to calculate earth fault currents, earth fault voltages, calculate the current distribution of these earth faults to make up a good earth fault protection. So, a practitioner sees his network as it is indicated here. We have a substation, we have branches going out, which may be made up of cables, of overhead lines, or a mixture of these. We have a fault on one of these lines, and the practitioner demands, I want to have a clear indication that this line is faulty. On the theoretical side, the theory says, in order to calculate earth fault currents, one must calculate the series impedance made up of positive sequence impedance, Z1, negative sequence impedance, Z2, and zero sequence impedance. And just to give you some relief, the zero sequence impedance is the most important one, and I will in the future omit the other two impedances, which make up only something like an error of 2%. So now this zero sequence impedance, as indicated in red, is represented in a more detailed way. It consists to the right side of the healthy network, that means the capacitances ground to line. It is made up of the arc suppression coil or Petersen coil, and also the return path is important. And the whole zero sequence system consists of the sum of all current carrying components that lead the earth fault current from the fault point back into the otherwise perfectly insulated electrical system. And this can be calculated. So these are the factors that are important: the healthy network, the arc suppression coil, and the line impedance. Let's start with the solidly grounded neutral, as it is known to everybody of us in the low voltage network as a start. So in a low voltage network, we have a transformer, we have a line, we have a neutral return path, and we have a fault. Now, this is also well known. We have a current loop that is made up of 2 times the lead impedances and the fault impedance, and the formula of the whole thing is given below. This known circuit is now redrawn to make it more compatible with the system of the symmetrical components, which are given here in a reduced form. And by the way, the outcome of course is the same. This circuit consists of the phase voltage as the driving force. It consists of the arc resistance or the fault resistance, and then we have the lead going forth and back. This already comes very close to the low impedance grounded neutral in medium voltage networks. So here we have the network consideration, which is very much the same, except that we have a current reducing or a current restricting resistor Rn between transformer neutral and ground. So the fault impedance is made up of these elements, and we should pay a little special attention to these ZL and ZM. ZL is the line impedance, as we know it, and Zm is the part of the loop impedance that is underground, so to say, which is the mass impedance. And this mass impedance is usually defined by this earth current return factor K sub 0, which some of you may know from distance protection. So this is the proportion of the whole loop that can be attributed to the return path. And the whole current in this loop is given by the next formula. To redraw this physical path to make it more compatible with this reduced symmetrical component system, we have the same circuit, and the value of course is unchanged. Now let's start with the insulated neutral, which is the first step to understand the resonant grounded grid. So again, we have the network configuration, where in the neutral of the transformer there is just nothing, which means it is an isolated neutral. Then we have the currents that from the fault point go back into the otherwise perfectly insulated system, which is the capacitive currents of the healthy feeders and of the faulty feeders. And these add up to the fault current, and this is the representation in so-called reduced symmetrical components representation. When we put this physical circuit into the reduced symmetrical component system, we see again we have a driving force, the phase voltage. We have an arc resistance which maybe restrain the current, and then we have the return path through ground, which is made up of the capacitances. Now the question is, how big is this value of these capacitances? And the good news is we know the answer, because we know that this current is just the capacitive ground fault current. So this reactance is given by the formulas, as you can see to my right side. And then the current is just given by the geometrical sum of these two, that is the resistive and the reactive component. So this is a formula without any factor of 3, which some of you may attribute to the symmetrical component system. It's a very clear and straight approach. So the next one is the resonant grounded neutral, in which I follow the same methodology. That means we start with the network configuration, go on to the physical paths, which are, in addition to the capacitive currents in red, augmented by the current through the arc suppression coil. And these currents mix and get together at the fault point, and they make up for the fault current. And now we go into the reduced symmetrical component system, which is made up of the driving force, the arc impedance, and this parallel circuit, which is something like a current brake, so to call it. It reduces the current, it is a throttle. And what is the value of this impedance? We know it. We know that this reactance is designed in such a way that it allows only for a small proportion of this capacitance currents to go through. And this is given by the phase voltage divided by this residual current, which is made up of the detuning, which is usually given by the factor of V. And the whole current is just made up of this. Again, no factor of 3. And by the way, this is very accurate. The accuracy is approximately 2% in real-world networks, so we can be happy with this solution. The next scheme I would like to introduce you, how we can calculate it, is the short time low impedance grounded neutral. Sometimes it is desirable or necessary to add additional resistances into the neutral current path, thereby increasing the resistive proportion of that current in order to help protection to find the fault. Again, the network consideration. Now note that we at the far end of the network we have an additional resistor which is switched on and off. And again we have these components, capacitive, reactive, and here an additional component which is a resistive component. All these 3 components make up the final fault current. Now we go for the calculation into the reduced symmetrical component system. Again we see what we already know. The phase voltage is the driving force, the arc resistance. Then at the far left we can see this parallel circuit make up of capacitances and the arc suppression coil reactance. Also the short time low impedance resistor is indicated, and between the fault point in F and this parallel circuit we see now that the line impedance plays in this time quite a considerable role. So again, this is the neutral system, and we concentrate again on this role of the line impedance and the return path for this line impedance of the faulty line. Again, as it was before, we have this earth path matching factor K sub 0, and the whole current is now made up of the voltage divided by the circuit plus an additional impedance that is inserted. This is the line impedance and its return path. Again, we have a solution, and it is very accurate, by the way. And that was today's lecture about earth fault calculations. I thank you very much.